Here's a little project I've been doing for fun, a little something on the side. All the details are up here on GitHub, and I'll include a link, but I'll just give you the quick version. Just getting started. It's about data compression, it's about image compression. Here's my first reference image. There's more coming, but this is what I had handy. This is a thumbnail from a different project. So every pixel here is 4 bytes. 1 byte for the amount of red, 1 byte says how much green, 1 byte says how much blue, and then there's the transparency, or alpha. So let's look at these 4 channels separately. And let's start really simple with the red. We have a whole lot of zeros. We have, looks like 500,000 zeros. The relative values are right. This chart has some problems. I don't know about this scale. But in any case, a whole lot of zeros and a decent number of 255s, a decent number of places where it was completely on, more than I might have expected. And in any case, it's kind of bunched up. There are some values that are more popular than others. There's no zeros. You just can't tell from the scale. Things get too small. But the important thing is that certain items are just so much more popular than others, and that leads to a certain type of compression called entropy encoding. And if I do that, it's a standard operation. If I just take all these bytes and give them to the entropy encoder, it would cost me 1.3 megabytes just for this. Then the question comes up, what if you take those bytes and all you do, you compare each one to the previous one and ask how much did it change? And wow, this was already kind of spiky, and spiky is good. Spiky means I can predict the data and I can compress it cheaply. And sure enough, we have this huge spike with almost everything, 1.6 million. These were the number of times when the red value was exactly the same as the red value of the pixel immediately to its left. And then it goes down a lot, but +1 and -1 are huge things, and then -2, and it trails off. There's some structure to this if you zoom in. And there's actually 100 values out of these 500 and some odd that are 0. But again, there's some weird structure here. You do have to deal with the other values. In any case, the entire cost for this is some 328,000 bytes. And then optimistic RLE. Short version, I want to take all these zeros and take a closer look at them. I think they're going to be clustered a bunch in space, so you should be able to say, hey, there's 10 zeros in a row, there's 10 bytes in a row that are exactly the same, or 100 or 1,000. And again, I'm just doing rough numbers now to see if this project even makes sense. And I said, let's just assume that all of those zeros disappear. So now there's one extra item with no cost to it, no entries. So it only costs 142,000 bytes if I get rid of that, so less than half. So that's pretty good. I got the file size down to less than half of what it was before. Green, very similar picture, have a weird spike in the middle here, but otherwise very similar. Again, that's the whole point of this data. You would expect it to look similar. Otherwise, if it was only this one picture, or if it was only one color channel for that matter, it wouldn't be interesting. The whole point is that everything is a bell curve, or bell curve-ish. And then what's this? This was 281,000. Yeah, so we're cutting the cost by more than half. Blue, again, very similar. Very, very similar. And then the alpha channel. I didn't do anything special. I think PNG has some special mode in the headers that says just to skip the alpha channel if you don't need it. But the way the software works, just my idea of entropy coding, it doesn't need anything special. It's just going to be very cheap. A cost of 8 bytes, that's basically the overhead to say nothing but this one value. Everything was 255, completely opaque. And then this is even simpler. Everything was exactly the same as the byte before it, and again, to say I got 1,000,000 of these, 1,000 of these, whatever, they're all the same. There's no real cost. There's just the one-time setup. And an even less interesting chart. There's no data left. Alright, so what's the summary? If I just looked at the bytes, which is probably what it takes to store this thing in memory when it's actually being displayed, if I just look at the bytes, it's 8 megabytes. When you save it as a PNG, it gets down to less than 1/10 of the size, 700,000 bytes. 8.5% of the original size. Then, just for fun, I said, what if we went through the bytes just one at a time and we looked at them and sent them directly to our entropy encoder? And, well, it cuts it down 44% of the original uncompressed size, but 500%, so 5 times as big as the existing standard. Then we get to something more exciting, and this is what the QOI was pushing, and obviously they didn't invent it, but they were just reminding me that it could be this simple. So what if I just looked at all those differences? Well, the total cost of all those things was 896,000 bytes. And, well, that's about 11% of the original file size, so a lot better than my byte compressed thing. And it's still not great compared to PNG. It was about 27% bigger. So that doesn't mean it's not interesting. It just means that we're not done yet. And why would we be? This was very quick. This was just a very first look. So how much more could I gain? As I said, the next thing I would do is look at all those things that say nothing's changed and ask, how many of those happen in a row? Because that's just an easy thing to compress. And optimistically, I could get down to about half the size of PNG. And again, that's the bound. That's the most that I could get. But it's saying that it's interesting and it's worth looking at. So mostly I've been posting pictures of attractive, bright animations, but there's other projects going on. Thanks for taking a look. Like, share, and subscribe. See what I do tomorrow.